Hello everyone, I am Shitij and today we will talk about friction. It's a very important topic, small topic, but very important because it lays down the basics for every coming question, whether it be NEET or JEE. So we will be covering a lot of subtopics today, right? The main thing is that after today you will likely be able to understand so many concepts much better, right? Okay, so first we will start with contact forces. So each topic we cover today, we will do it a bit faster, okay? So I'll just write down the names now and we'll just start, okay? So contact forces, friction, okay? Friction, and obviously this is the main topic, right? Angle of friction, okay? Angle of friction, really important. Again, types of friction. Yes, there are types. I really don't want to make today's video very lengthy. And very interesting part, atomic outlook, right? So this also we have three things which we'll cover here, right? Y mu s more than mu k, right? Self-adjusting and heat, okay? Laws of friction. Even friction has laws, apparently. Tension versus friction. It might look like a lot, but it's very small short topics, okay? Very small short topics. Friction on inclined plane, I'm not writing down the numbers so as to not make you nervous. Okay, we'll be moving a bit faster today, you know. Have I pressed record though? Yes, sorry. Always have to check because you know what happens is oftentimes you end up wasting a lot of time and then you have to record again and it's a pain, okay? Rolling friction, right? Rolling friction. Pushing versus pulling. Right, general things, right? Tutti, string into blocks, okay? String into blocks, and these last few bits, Okay, these last few bits, they will set up the second part where we will be doing many questions. So it's very important that you focus on them, right? Actually, this whole topic is very important, so I really advise that you don't skip anything, and every time you require a pause, just pause the video. Okay, let me count. Am I missing something? No, not really. Okay, so before we begin with friction, I have an interesting question for you. So we did laws of motion last time. Okay, okay, so try to do this with me. Okay, try to do this with me. Imagine there is this figure, right? Sorry about that. There's the surface, there's this clamp, this is a pulley, there's a rope. Okay, this rope is stuck to this wall. Right? Let the mass of the weight be m, small m, capital M, sorry, and mass of the pulley is small m. Alright, now look at this figure. What will be the force? What will be the force that this clamp is exerting on the pulley? Okay, now there will be a timer of 5 seconds. After that I will teach you. So the timer has ended. Okay, so first things first, tension here, right? Tension here, tension here. Okay, all right. Apparent the weight of this mass mg, right? Now if you look here, you can see tension is equal to capital M into G. All right, and over here we have a small free body diagram right at the pulley. Okay, so there is one force T going in this direction, and perpendicular to it we have two things. Right? We have the tension itself. Okay, and we have mass of the weight of the pulley. Okay, now why have I done this? Because we have to find out the force which the clamp exerts on the pulley. And if you remember the third law, okay, third law of motion, we have an action reaction thing. So therefore the force that the pulley that the clamp exerts on the pulley is equal to the force that the pulley is exerting on the clamp, right? So how much force is the pulley exerting on the clamp? So one component is this, the tension itself, and another component is tension and the weight of the pulley, right? Now you have to find out the resultant of this. How do you find out the resultant? Simply these, now these are perpendicular, so you can imagine that these are coordinates, right? These are coordinates. So therefore F net will be equal to what? So you take this component T square plus T plus small mg square, okay, and under root of this. Now this was the first equation, this is the second equation. So from now have a look at this first. Okay, from 1 and 2, what do you get? F is equal to, now as you can see, G is there in each component. Okay, so you take G outside, G is square, so therefore inside you get m square plus m square. This is your answer. All right. Sorry, I think I went a bit out of frame. Please write it down. Okay, let's begin with the class now. We will be going on quickly, moving quickly and quickly and quickly, alright? So, contact forces. What are contact forces? Contact forces are those forces which appear simply when because of physical contact or during the when the objects are in contact. So basically, if you start a contact, if you initiate a contact, or during that contact, whatever forces are there, they are called contact forces. So for the benefit of our class, the contact forces will be normal reaction, weight, okay, tension, and friction. But whenever we will mention it in exams, we will only talk about two things. First is the normal reaction, and the second is friction. All right, okay. You must be wondering, why is tension contact force? You can search it or think about it really. This is your, I'm really sorry, imagine this is your rope, right? So it's being pulled downwards by some weight. Why is that happening? Because of force, is because of weight is acting on it. And why is that weight acting on it? Because of this contact here. That's why it's a contact force. Okay, now contact forces have a very different thing. They don't act because of distance. Like, so for example, we have electromagnetic forces. They will have some kind of distance component on them, on which because of which they will vary, right? But contact forces don't do that. Okay, this is very important to understand. Let's talk about friction. Okay, so to understand friction, this particular diagram will be very important to you right now. Right, and okay, and what else? Yeah, so okay, actually will be in this direction. Yes, let me draw it again, sorry about that. So normal reaction here, friction here, force here, right? Okay, now it's all right. Okay, sorry about that, because I have to move fast, so a little bit of issues. Okay, so what is friction? Friction is a contact force that tries to oppose relative motion between two objects in contact. Okay, relative motion between two objects in contact. So one object is this box, right? This box. Another object is this floor. So these two are in contact. Now this force is acting on this box, trying to push it forward. So as a result of it, what happens is this object is moving forward, right, and there is another object below it, right, which is providing the friction. Why is it providing the friction? For it, this is moving forward, so it will try to pull it back, so therefore this opposite force will apply on it. This force is the friction force. Now all the forces occur in pairs, therefore the friction force that is applied from B onto A, similar force A will apply onto B. Okay, A will apply onto B. Now look here for a second. Imagine, now to B, A is in relative motion, right? It is moving forward, but if you look at from the reference of A, okay, and if you think about A looking at B, so for it is at rest, and B, for it B is moving in this direction, right? What is happening is, now it will provide a friction onto B, so that it will pull it in the opposite direction. Therefore, even when friction is there, it occurs in action reaction pairs. Okay, and this friction will be equal to this friction. All right. Okay, so that is what is friction. It will only happen, it will only appear, friction will only appear when there is a tendency of motion, or motion is there, right? So it will oppose that. Okay, if motion is not there, then friction will not be there. Okay, this is very important. Okay, so angle of friction. Now, as I said before, contact force, when we talk about contact force in the exams, it will mean two things: normal reaction and friction. Okay, what that means, basically contact force is the resultant of these two. So this is the contact force. All right, so what is the contact force? It's basically R here. Okay, right, and what is the angle of friction? It's theta, but when we call it the angle of friction, we represent it as lambda. Okay, so okay, simple. Okay, angle of friction, types of friction. Let us first look at kinetic friction. There are majorly three types of friction: kinetic friction, sliding is a kind of kinetic friction. Okay, we have rolling friction and we have static friction. Okay, there are three types of friction when we talk about exams. So what is kinetic friction? Whenever an object is moving, the friction which tries to oppose that motion, okay, that is the kinetic friction. That's all. Okay, so suppose this object is getting a force F and it's not balanced. What that means is, basically the acceleration becomes non-zero, therefore it acquires some non-zero velocity. So at that point this friction provided will become kinetic friction. Okay, very simple. So that's what kinetic friction is. Talking about static friction. static friction will appear whenever there is a tendency of motion. Very fine distinction between static and kinetic. So suppose this object, this force is getting applied, right? Force is getting applied to it from left to right, right? But object is not moving, still friction is there. Why? Because if friction were not there, it would move. That's why static friction is kind of a variant of kinetic friction, but not really. So whenever asked, static friction is something which opposes tendency of motion, not motion, tendency of motion. So in whichever direction the motion is supposed to occur, there is a tendency of motion to occur in that direction. Static friction will oppose that direction. Okay. Right. See, as I told you, these are very small things we need to cover before we move on to the meaty part. Okay. Now let's put on a microscope at this surface and really think about what friction is. So look here, let's make it bigger. Okay. Okay, so what happens is, surfaces which, even though which appear smooth, they are not actually smooth. So what happens is, there are some irregularities. As you can see, think of this as the box and this as the floor. Okay, so even though they are close by, they are not actually touching. Okay, so what happens is, over here, right here, the atoms, I'll use a different marker for both. Okay, so assume these are the atoms of the box, right? And these are the atoms of the floor. Okay, so what is happening is these surfaces, when they are in contact, the kind of bonds form between them. Okay, now these bonds, when they get formed, right, they try to maintain these bonds so that they don't get broken, or they don't change shape, or they do not denature or decompose, right, or deform, right, in any way. So when we apply force, so a tangential component is applying to this part, right, and what happens is, this is moving in this direction while the floor is still there, it's not moving, so this bond gets lengthened. So what will happen? This bond will try to pull it back. That's what provides the friction. Okay, that is what is providing the friction. Okay, so as a result of that, there are several things that are happening. So the first thing, which is very important to think about, static friction is always more than kinetic friction. Always, in the sense, I will explain later. Okay, but we need to understand this first. Why? So right now this box is at rest. So the box and the floor have a full chance to form these bonds, right? To form these bonds. So these bonds get formed, and when I try to push them, these bonds are really strong. So imagine when you were younger, your parents must have told you there is strength in unity. So you take 5-10 pencils, you try to break them, and they won't break. But if there are lesser than that, it will become easier to break. So similar thing. So more bonds are there when you are at rest because they are fully formed, right? but when you try to push them, it won't push easily. But once it starts to move, imagine it's moving, right? So what is happening is this bond gets broken. Decomposition is trying to happen. As a result of the decomposition, this bond is broken. A second bond is trying to form. Now it's kind of formed, but it's not that strong because it's not fully formed, and it's still moving, lengthening and shortening, because of as a result of the movement. So here, if you notice, there are 5 bonds here. Imagine these were at rest. So just for an example, the 5 bonds were there at rest. So when the object is moving, there might be 1 or 2, and even they don't have a fixed length. So bond length is continuously changing. Therefore stability is less and it's easier. Therefore static friction is always more than kinetic friction. Easy? Okay. One thing that is important about static friction is that it is self-adjusting. Self-adjusting. What that means is, the more force you apply onto it. So imagine we are in this situation, right? The more force you apply, the more it will oppose up to a certain limit until the object starts moving. So if you apply lesser force, lesser number of bonds will be able to be broken, will have a lesser number of bonds will have a tendency to break. That is why the force to oppose that will be lesser, right? Okay, so that is why static force self-adjusting. Static force is self-adjusting up to a certain limit, and that limit is called limiting friction. Okay, limiting friction. And kinetic friction will always be lesser than this limiting friction. Okay, now you got it? Okay, now let's move on to the third portion of this atomic outlook, that is heat. How does friction help in producing heat? Okay, now look at these surfaces, right? Imagine these two surfaces are there. Now I have locked them. These bonds are locked, right? So as this bond is moving forward, this bond, it's moving in this direction, right? But imagine if I am rubbing my hands, what is happening? Once this bond is moving forward, and the second time it's moving back. Okay, so the movement is to and fro, right? So what happens is, because of friction, vibrations get produced at these edges, right? And as a result of these vibrations, these atoms, they start vibrating as well, right? So these atoms are vibrating. Now think about it. What happens when objects are heated? They start vibrating more. So that is how heat is produced as a result of friction. So what you are doing is, you are basically using your mechanical energy to do some work upon two surfaces, right? And a portion of this work done, is getting used from mechanical energy, and it's getting converted to heat energy due to these vibrations. See? Simple. Okay. So laws of friction. I hope you are able to understand what I'm explaining here to you, right? I hope it's easy. I have worked very, very hard and many days to make sure you understand this topic, right? So laws of friction. There are 4 laws. Okay. First one, the kinetic friction is represented as Fk. Okay, small f. Okay, so kinetic friction is directly proportional to the normal reaction. Okay, that is the first law. So as it's proportional, this Fk ends up having some constant to get a formula. So that constant is called the coefficient of kinetic friction, mu k. Okay, so this ends up being the formula for kinetic friction. So the first law is kinetic friction is directly proportional to normal reaction. Second, static friction is also proportional to normal reaction, but it's less than equal to static. The static friction is less than equal to the product of the coefficient of static friction multiplied by the normal reaction. We discussed, right? Static friction is self-adjusting. We had an atomic outlook at that, right? So this is the formula for that. So when the static friction equals the product of the coefficient of static friction multiplied by normal reaction, right, then it's called limiting friction. Okay, limiting friction. Before we move on to the third one, please remember, friction is a component of contact force. Okay, even normal reaction is a component of contact force, right? That is why there is a kind of codependency, right? Codependency. Okay, third one, direction of friction. The direction of friction will always oppose motion or tendency of motion, right? So this block was there, the force is applying from left to right. Okay, from left to right, this is the floor. Let's assume the coefficient of friction is mu. Forget about coefficient of friction, just there is some friction F. Okay, so now force is applied in this direction, so the tendency to move is in this direction only. So then static friction will be in this direction. So tendency to move is from left to right. So friction is getting applied in direction right to left. Okay. Similarly, if let us assume that this force was enough to cause motion, and this acquires a certain velocity v from left to right. Okay, from left to right, then the friction getting applied becomes kinetic friction from right to left. Simple. Okay. Fourth law, this is an interesting one. Friction does not depend on area or velocity of object. No matter what the area, surface area of the objects in contact is or are, or whatever their velocity is, it will not depend on that. Friction will not depend on that, regardless. Okay, these are the 4 laws. So in the exams there will be a conundrum you will run into. Okay, sometimes, not always. Okay, So think about it. There is this wall, okay, there is a block on the wall and there is a string connecting the block to the wall, okay. Now how will you calculate the force? Will it be F is equal to T first, or and then you will calculate friction, or F minus F is equal to T? Which one do you think is correct? If you remember in NLM, in laws of motion, I said that spring and rope and string, they can change their tension instantaneously. So whatever force will be applied, tension will be as a result of that, right? But there is a discrepancy here. When we talk about exams, as I said, friction will oppose relative motion, right? Friction will oppose relative motion, but as a result of that, always and always in exam, you have to take in account friction first. Friction first. For gym there is fitness first. For physics there is friction first. Just kidding. Just kidding. Okay. Okay. So this is tension versus friction. Reality might be different or is different, but for your exams this is important. Okay. Friction on inclined plane. Okay. Please forgive my diagram. Let me make it again. Doesn't really matter. Okay, much better. Much cleaner. Now it's better, right? Okay. There is this inclined plane. Okay. There is this block, has a mass m. Now this diagram will be important for a bit longer. Okay. Let's say this is alpha, not theta. Okay. So the weight is acting downward, right? The weight is acting downward. Okay. Now there is some friction here. There is some friction here. Okay. So if you have studied kinematics, you know the block will move down with a force mg sin theta, right? And the weight exerted on the inclined plane is mg cos theta, but in this case it will be mg sin alpha, because we have taken it as alpha. Mg sin alpha and mg cos alpha. Cos alpha. Okay, right? Okay. So what is happening here? Mg sin alpha is in this direction, so friction will try to oppose, right? So if this object is at equilibrium, we will say F is equal to mg sin alpha. Okay, and alpha we will work on it now. So at equilibrium, friction is equal to mg sin alpha. That is, equilibrium is there, block is not moving, so F is static friction. So at that point F is equal to mg sin alpha. Okay, now here comes the crazy part. Now this is some angle alpha. Right now this block is not moving. Okay, so if I don't do anything right now and just increase the angle, so the angle at which this block will start slipping, right, will just start slipping, that will be called the angle of repose. Okay, angle of repose. Now think about it. Isn't alpha really the angle of friction? Now, how did you get mg cos alpha here? Because this angle was alpha, and okay, this is normal, right? So this is alpha, this is the contact force. So the angle of friction is the angle between the normal and the contact force. So alpha is here. So alpha is really the angle of friction. So the angle of friction at which the object just starts slipping on an inclined plane is called the angle of repose. Fine. Now mg sin alpha is the force with which it is moving forward, right? And normal reaction is what? Mg cos alpha. Now, what we need to think about, what happens to the contact force as we increase the angle of repose, right? So let us say that let's just assume alpha is the angle of repose. Okay. Oh, one thing I forgot to tell you, that's my mistake, I'm sorry. So when we talk about angle of friction, so let's say theta is angle of friction, so tan theta, it will be equal to the coefficient of friction. Okay. Now this coefficient of friction I'm sorry, I'm not okay, alright. So this angle of friction tan alpha. So this value of mu, this does not change based on the angle. Okay, mu remains same. Mu is we will talk about how it changes, not right now. Okay, so tan alpha is equal to mu. This was what you needed to know. So we are at a certain angle, so till theta is less than alpha, okay, till theta is less than alpha, contact force is constant. Why is that? So contact force is a resultant of friction and normal reaction. Normal reaction is what? Mg cos theta, and sorry, mg cos theta, sin theta, yeah, sorry, normal reaction and friction, right? But when you think about it, before theta, before alpha, friction is opposing what? Mg sin alpha, right? Mg sin theta. So therefore friction is mg sin theta, and this normal reaction is mg cos theta, right? So contact force is what? Square root of this, right? But what is this exactly? It's just mg, right? That is the weight. So up until we reach the angle of repose, contact force is just mg, right? But once we start moving beyond the angle of repose, it starts decreasing. What happens? The value of friction starts to decrease. Value of friction was decreasing anyway, okay, but after that certain angle, that angle is so much that the total value of the contact force will start to decrease, okay. So what is happening then, that r, this mg sin theta, it becomes the original value mu mg cos theta, okay, plus mg cos theta, right, because our normal reaction is what, mg cos theta, right. So and our friction is mu n, right. So mu mg cos theta plus mg cos theta, we square all of this. So what is happening? Mg comes outside, right. Mg comes outside, cos theta will come outside, and you get m plus mu square, right. So as you can see, as the angle is increasing, cos theta gets decreased. So cos theta is decreasing, therefore contact force is decreasing. Okay, simple. So what do you have to write down? Alpha is angle of repose. So when theta is less than alpha, contact force is constant, right. That is case 1. When it's greater, sorry, I tend to mess up these signs. When the angle is greater, when theta is greater than the angle of repose, then it starts to decrease. Okay, I hope this much is clear. Friction and angle of repose. Okay, so talking about the coefficient of friction. The coefficient of friction is a property of the materials that are in contact. What that means is, it does not depend on anything other than the materials itself. Yeah. So it will only change based on two main factors. If you change the material, or if you somehow modify the smoothness of the surface. Okay? These are the only two ways. So for example, you have a question. We are not going to solve this one, just giving an example, that a wooden crate moves on a steel surface, right, and then there is a steel block that moves on a steel surface. So they will have different friction. And also, if I say in a question that, okay, I have a steel box A and its surface is unsmoothed and it's moving on the steel floor, and now they have smoothened it and smoothened the surface of the block, and then now they are moving it on the floor. So the friction, the coefficient of friction will be different in these cases. So you will have to bear in mind to the question. Okay. What is rolling friction? Rolling friction is kind of like kinetic friction, but it's not the same. So what happens is, think about your car, it's moving, right? It has a wheel, okay? Sorry about my drawing. right? It's this wheel, right? So when we talk about the wheel, this wheel, when it moves on the floor, there is a very small point of contact with the floor, right? And all the weight is acting on that. So as a result of that, there is more pressure on the floor. So there happens some depression on the floor. Okay, let's call this depression KL. Okay, depression. Now the tire is acting on the floor, the depression is there, therefore it's the bonds are now getting formed there, right? As the pressure is more, so same pressure is acting back on the tire, as a result of which it's getting compressed, right? And now it entered the depression and now it has to exit this mount. Let's call this area mount, right? So during the depression, these bond, right? So this tire simultaneously, it has to enter the depression and it has to simultaneously leave the mount and prick the bonds, right? So this is what provides the rolling friction because of this pressure. Now, if you fill the air in these tires, right, and the tires are bigger, so this friction, this pressure on this tire that gets pushed back, it kind of decreases, and as that decreases, the pressure it provides also kind of decreases. So therefore a tire which has more air, it will have lesser rolling friction and the car will move smoother. Okay, simple. I hope you understood rolling friction. Okay, let's talk about pushing versus pulling. Now imagine you have this block, some mass m, okay? Normal reaction is not just dependent on the weight of the block, okay? So right now this block is lying on this floor and the weight is mg, therefore the normal reaction is what? Mg. But if you have to, let's say, push this object, right? Now this block is lower than me, right? So I will push this object at an angle. So the force I apply, it will be at some angle to this block, let's say theta. This is the force, okay? But I have to move this block in this direction, right? In this direction. So the force that is getting applied in this direction is what? F cos theta. But two things. First of all, this force is getting broken down here. Now there is one component F cos theta, but there is another component F sin theta. This is getting applied in the downward direction, right? And as a result of that, it adds up over here, right? And as I mentioned before, static friction is self-adjusting. So this kind of increases the friction which is applying, which is opposing this block. Opposing this block's is tendency to move as a result of this. How? Because mg plus f sin theta becomes the normal reaction. This increases, so this increases, and what is friction? Friction is what? Mu n. So even if, let us assume it's moving, Fk is also equal to this, right? Fk is equal to this up until it starts moving. Fs will also follow this formula. So no matter what you do, if you are pushing from above, you are making it harder to move the object, right? Okay, so pushing will make it hard. Now what if I pick up this object from behind like this and I pull it, right? Then this force is applying in this direction at some angle theta 2, let's say that was theta 1, right? And this is F2, this was F1. Okay, now what is happening? Now we have this component F2 sine theta. Okay, it's going in this direction, therefore it is reducing the normal reaction. Really sorry. F2 sine theta, this is reducing the normal reaction. Okay, also as it's reducing the normal reaction is reduced, as a result of that friction is reduced, so it becomes easier to pull that object. Okay, but one more thing to remember, if you are a gardener, you will need to push it down. As a result of that, friction will be more, so friction is opposing, therefore it will be easier to cut the grass. Okay, okay, now imagine there is this box. Okay, right, there is this box, some box. The force that is applied, okay, it's equal to 2t, right? T is what? Time. How will we plot the acceleration of this box? So depending on time, the force is increasing, so that force will increase until that force is increasing anyway. So up until this force is equal to the limiting friction, this box will not move. But as more time passes, it will be more than that, so therefore this will become greater than the kinetic friction, then it will start moving and it will keep on accelerating. Okay, because the force is increasing, right? So let us say time is on the x-axis and acceleration is on the y-axis, right? So up until certain time t, this object is not moving, so acceleration is still here, and then it starts moving, it starts accelerating this, right? But point to note is the acceleration will not start from 0. Why? Because kinetic friction is less than static friction, so there will be a slight jump. Okay, so this will be the graph for this situation. Just a question to explain. Okay, now we come to the conceptual part of the concepts. We are done with the theory. Okay, okay, now this is an interesting thing because these kind of questions come in JEE as well, and as well as NEET, right? So please maintain your attention for a little more time, right? Okay, Okay, I will not explain this using theory. I will have just taken an example and I will use it to help you solve this question. So what we have to find out, basically the tension in the string and the friction at both of these places, right, below both of these blocks. So as you can see, let's call this block A, let's call this block B. Okay, so block A is getting pulled with a force of 15 Newton, block B is getting pulled with a force of 25 Newton. Okay. Okay, this has a coefficient of friction of 0.5, block A, and block B is 0.4. So let's first see whether this system will move or not. Okay, so let us say, think of this system as one block. Okay, 7 kg. Okay, what will the friction be on this block? What will the friction be on this block? The friction on this block will be so 2 kg, right? So friction will be 0.5 into 20, so 10 Newton, right? Am I correct? 20, yes, 20, yeah. And here it will be 50, 5 into 4, 20 Newton. 20 Newton. Okay. So this is the first step, right? 7 kgs and friction is 30 Newton, right? Limiting friction is 30 Newton, right? Now 15 from right to left and from left to right 25. So what is the net force? 10 Newton. So we have available 30 Newton of friction and we are providing only 10 Newton of force. So therefore this system will not move. Therefore this system is at equilibrium, right? So first thing we answered, equilibrium. Second, now as this is at equilibrium, one of these two it will have limiting friction. Both of them can have, but at least one will have, right? And as limiting friction is there, this string will have some tension, right? Okay, fine. Now let us assume that this box block A is providing the limiting friction. So movement towards, think about it as in terms of free body diagram. Movement is in this direction, therefore friction will be in this direction. How much? 10 Newton. So FA, let's say 10 Newton is here, right? 10 Newton is here. Okay, limiting friction is here, right? So 10 Newton is opposing here and this system is at equilibrium. So to make it at equilibrium, how much tension we need? 15 is here, so we will have, let's say, how much is left? 5 Newton. Okay, now this is just an assumption right now. Okay, so 5 Newton here, right? 5 Newton here. How much is pulling? 25 Newton. So 5 and 25, how much of friction do we need? 20 Newton. Is 20 Newton available? Yes. Therefore this solves the question. So we have T is equal to 5 Newton, FA is equal to 10 Newton and FB is equal to 20 Newton and system is at equilibrium, right? Simple. Now think about it. If it were 12, would this work? Definitely this would work. It was lesser amount of friction would be required on this side, right? But if it were more, let's say 18 Newton, right? Then what would happen? So 18 Newton is here. how much limiting friction we have? 10 Newton, right? So how much this will become? Tension will become 8 Newton. 8 Newton, right? 8 Newton is here. So 8 Newton here, 25 Newton here. Yeah, that is also working. Sorry, not 18. Let's say 12. 12 Newton. Let's do it 12 first. 18 is here. 8. Oh yeah, it was right. Sorry, it was right. 18 is there. So sometimes I tend to doubt myself. So 8 is here, right? Newton is here, 10 is there, 8 is there, so 8 is here, right? Right, so we need 17 Newton here, 17 Newton will be here. This will be balanced. So let's take 12 Newton. Newton. 12 Newton is here. How much do we need? 18 Newton is done. 12. So 12 and we have 10 here. So 10. 2 is here. 2 Newton. 2 Newton of tension. Therefore this becomes 2, right? So 2 is there. 2 is there and we have 25. Can we provide sufficient friction here? No, right? We need 23 here, but we have only 20 available. Therefore, we have to flip the thing, right? The limiting friction cannot be here. So then the limiting friction has to be here. So then we flip it around. Let's say 20 Newton of friction is provided here, right? This is 25. So 5 Newton of tension here, 5 Newton of tension here. So 12 minus 5 is how much? 7 Newton. Therefore, now this becomes the answer. In this case, FA is 7 Newton, FB is 20 Newton, and in tension we have 5 Newton, right? Simple. So, similar question we have seen in JEE, right? For 10 marks. Okay. Please forgive my horrid drawing, right? Okay, now you can write it as this, because this pulley is frictionless. Okay, we have 5 kg here. Okay, right? 0.5 mu, 0.5 mu. Okay, now what is the normal reaction? Normal reaction is mg cos theta, right? Mg cos theta. So mg cos theta, cos 37 is how much? Is 4 by mg cos 37 is 4 by 5. So mg f limiting will be 0.5 into 5 into 10 into 4 by 5, right? 20. Yes, 20 newtons. Here is what? 0, this will be 3 by 5, 3, 15 newton. Okay, so these are our limiting frictions in this, right? What's the force that's getting acting? So here it's mg sin, so 0.5 into it's 15 newton, and here it's 20 newton, right? Okay, so we got the forces. Because it's mg sin theta, right? Mg sin theta here, mg sin theta here, right? So we have total available friction 35 newton, okay, and we have a weight of 10 kg and total of 5 newton of force. 35 newton available friction, 5 newton force, therefore it will not move, so it is at equilibrium. Now let us say this is at this box, it has limiting friction active, right? So T is here, right? So 20 newton of friction right here, okay. This cannot happen. Friction cannot be more than the applied force, so therefore limiting friction has to be here, 15 newton, okay. So 15 newton of friction is there, 20 newton is there, tension becomes 5 newton, right? 5 newton is here, 15 is here. How much friction is available? 20 newton is available, therefore 15 actual friction becomes 10 newton. So that's the answer. FA is 10 newton, FB is limiting, that's 15 newton, and tension is 5 newton. 10 marks, JEE exam, simple. Right? This is how we solve these string and 2 block questions. Okay. Let's go a little faster. Okay. So think about it. I am applying a force F to a block that is on an inclined plane. I am trying to move it up. What will be the range, not the force, range of force that I can apply that this box will stay at equilibrium? So case 1, mg sin theta is greater than the force, right? So let's make a free body diagram. Before that, normal reaction is equal to mg cos theta equal to, okay, yes, so we remember. So this is mass m, mg sin theta is in this direction, force is in this direction, mg sin theta is greater, so therefore acceleration is in this direction, right? Acceleration is in this direction, therefore friction is in this direction, okay. So MA is equal to mg sin theta minus f small f minus f. F is what? Mu mg cos theta. Right? And as it's at equilibrium, therefore this becomes 0. MA becomes 0. Equilibrium. So we get F is equal to mg sin theta minus mu cos theta. Right? Similarly, if mg sin theta is greater than f and smaller than f, sorry, then it will move upwards, acceleration will be upwards. Therefore f will be equal to mg sin theta plus mu cos theta. This gives us the range of the values of f. So from this to this, let's write it down. Mg sin theta minus mu cos theta mg sin theta plus mu cos theta. Right? This is the range that will keep it in equilibrium. Okay? Please write it down. Okay. Again, inclined plane, it will come many times. So think about it. There are two bodies, M1 and M2, right? Different coefficients of friction, mu1 and mu2. Generally, if there is only one block, right, A will be equal to g sin theta minus mu cos theta, mu g cos theta, sorry, mu g cos theta, right? Because acceleration does not depend upon the mass, right? Okay. Now, this is a general formula, but in this case, let's say this is mass A and this is mass B, right? So if mu1, okay, coefficient of friction of first one is less than coefficient of friction of the second one, right, that is B, what will happen? This friction is less, therefore this will move more, right? Therefore there will be no contact, therefore normal reaction will be 0. Therefore that general formula can be applied, that was A is equal to g sin theta minus mu1 g cos theta, right? This is theta, okay, in this case. But if mu1 is greater than mu2, normal reaction will not be 0, right? Normal reaction will exist. In that case, what will happen? Let's make a free body diagram of this mass A, right? So normal reaction is acting on this, right? Normal reaction from B. Acceleration is in this direction, right? Some friction is acting in the opposite direction to control it, right? And therefore, its own mass m1g is acting in this direction. But it's really this component g sin theta, right? So let's just say m1g sin theta. Okay. Okay. So m1a is equal to m1g sin theta plus n minus F. F is what? F is what? Mu m1g cos theta, right? So using this you can solve this kind of question. Okay, you just need to write this portion down. Everything else you're supposed to solve yourself, or you can rewind and watch again. Okay, imagine if there was some rope between these blocks. Okay, in the case of the rope the situation will be opposite. So if mu1 is lesser, okay, if mu1 is lesser, there will be some acceleration, therefore extension between the rope, therefore tension will be non-zero. Okay, but if mu1 is greater, therefore tension will not be there because they are moving to closer, therefore tension will be 0. Okay, simple. Okay, let's do a block over block problem. Okay, now this will help you understand how to solve block over block problems, right? The last thing which I will be covering will just be a formula. We will not be covering that one in detail. Maybe next time I'll do the derivation. Just I have included it just for the sake, if someone doesn't want to watch the second video which will create, right? So maybe I'll cover it in the next video, the last thing, but I will include the formula so that you can use it as a trick. At least you don't have to consult the second video, right? Okay, so what do we do in this case? What I want you to do is assume there is no friction here, right? First, okay, let us assume these both blocks are moving together. Forget everything. Let us assume these both of these blocks are moving together, right? So what do we have? Step 1, we have a 6 kg block, right? And the coefficient of friction is what? 0.2, right? And the force getting applied is 50 Newton, right? 50 Newton. What is the limiting force? So 6 kg, 60, 12 Newton. F limiting is 12 Newton, right? Right. So 12 Newton of force is here. So net force is what? 38 Newton, right? So what will be the acceleration? Acceleration will be 38 by 6 meter per second square. This will be acceleration max. This will be 19 by 3. Okay, right? So 19 by 3. Now if there was, this is the max acceleration for both blocks to move together. Okay, max acceleration for both blocks to move together. Now if there was no friction between the two blocks, then the first block, because of as a result of the force applied to it, would move forward, right? Now as it would move forward, therefore the acceleration would be in this direction, So the friction would be in this direction, opposite direction, right? Okay. So let's solve this. For this upper block, right, what is the limiting value for friction? So 0.5, 20, half of 20 is what, 10 Newton. So F limiting is what, 10 Newton, right? So how much is the acceleration? So 20 minus F, into 2, that is the mass. Acceleration was 19 by 3, that's the mass, right? So now this F should be less than 10 Newton, okay? Let's see. So F was here, F is equal to 20 minus 38 by 3. This comes out to be 22 by 3. FA is 22 by 3. Now 22 by 3 is less than 10 Newton. Therefore these blocks will move together, right? So FA is 22 by 3, and for the block below we have already calculated the friction which will be there, that is 10 Newton. We have the acceleration 19 by 3, solved. Easy, right? So first step, always assume those blocks are moving together, right? Let's do one last question for this block over block problem. Right? Let's say 40 Newton. 1 kg, 2 kg, right? Mu is 0.2. Let's say mu is 0.4. Okay. I'm sure this looks scary, but this is nothing but a block over block problem, right? Let's just transform this into the horizontal form, and how we will do this. Now we have to notice, in this case, the force that is being applied, that becomes the normal reaction, and the weight of the blocks, it ends up acting as the force that is moving against the friction. That's the only difference, right? So let's just do it that way. Okay. So limiting friction, let's say FB is what, 40 into 0.2, so 8 Newton. FA is how much? 40 into 0.4, that is 16 Newton, right? 1 kg, 2 kg, right? And how much are the forces? 10 Newton and 20 Newton. Now can this not be solved? Let's do the step for one again first. Think of it as one block. So 3 kg, right? 3 kg. Force is how much? 30 Newton. Available forces 8 Newton, right? So how much is the maximum acceleration? A max is equal to 30 minus 8 by 3, right? Okay. Now if we apply it there, right, this is the acceleration. So acceleration times the mass of this, right? FA is in this direction, so 10 minus F. Understanding how I got this? This acceleration I got from step 1. This is the acceleration, and then the equation will be A into M is equal to 10 minus F. So I just input that value directly here. Okay. So F is equal to 10 minus 22 by 3, right? How much is that? 8 by 3. 8 by 3, and how much is available? 16 Newton. Therefore this is correct. Therefore both the blocks will move together. Acceleration will be 22 by 3 meter per second square, right? Solved. Okay, this is how we solve block over block problems. Okay, hanging chain problem, just for the sake of covering it. So imagine there is a table here, okay, of length L, right? So some portion of this chain of length Y is hanging down this table. Okay, x plus y is equal to L. So how will you calculate the value of this portion hanging off? It's very simply y by L is equal to coefficient of friction upon coefficient of friction plus 1. That's all. We are not going to do the derivation of this today. Okay, I hope you had fun. We covered a lot of things today. We had covered a lot of theoretical things as well. So thank you very much. I will see you next time. Bye bye.